Welcome back to Math Methods Year 11 with Mr. Hanna. In this video we're going to be looking at sine and cosine graphs. Okay, so we remember that sine of theta, the angle, is the y coordinate. So if we draw our triangle here, this length here, this length will give us the y coordinate, which can be read off the y-axis there. So if we, let's plot a couple of points. So if our angle is 0, we've got a straight line across here, and so the y-coordinate is 0. So sine of 0 is 0. Now let's find a couple of other points. If we have going straight up, that's our 90-degree angle, or pi on 2, which is 90 degrees, going straight up, and there our y-coordinate is 1. So we'll reach 1 at pi on 2. So there's another point there. Then if we look across here, so this is where we have pi radians, or 180 degrees. Once again, there's no y value, well, the y value is 0, so sine of that is 0, so that's pi, and there's our point. And if we go straight down, that's 3 pi on 2 radians. And here, our y value is minus 1. So we've got minus 1 there, and that's at 3 pi on 2. So there's our next point. And then if we go 360 degrees, or 2 pi radians, get back to where we started, which is, of course, 0. So here at 2 pi, our next dot is here at 0. So now we can sort of join up the dots if we want to. We're joining up the dots, and we get this sort of curve. So let's sort of see that in action. We'll do all these smooth bits in between as well. So let's have a look at it. So here we go. This green dot shows where we are. So if we start here at 0 degrees, and you can see this point here on our sine graph corresponds to 0 degrees. So you can see that in our y-axis, we're at 0. And if we go up a little bit to, say, 10 degrees here, you can see we've moved along a little bit, and you see that blue line's the same distance as this little blue line. So it might be more obvious if I move around to, say, 45. You see that the size of this blue line here, the y-axis, is the same as this y-axis line. So you can see this sine graph being plotted as I continue to move this green dot around. So you can see that this point at 1 is the maximum value, and then it starts to decrease again, and then go down and back up and around. Now underneath you see we've got a graph of cosine of the angle. Now, of course, all cosine is the x coordinate, so you can see that in the red line there. So let me go back to the start, and you can see the cosine graph changes with the size of the red line. So it starts at 1, and as we go up in degrees, it decreases until getting to 0, and then goes negative to minus 1, and then starts increasing again. Okay. So you notice with both graphs, once I get back to 360, then I can continue. Once I get to 360, I can just continue around, and the angle just keeps on increasing. And what you see is the repeated graph. So it's a repeated sort of wave, if you like. So sometimes these are referred to as wave functions as well, because the shape is like a wave. Let's head back here. Okay, so our shape is like a wave, so it will just keep on repeating. So pi on 2 plus 2 pi will be the next point, which will be up here. So 2 pi plus pi on 2 is 5 pi on 2. 5 pi on 2. And the next point will be 3 pi, and then 7 pi on 2, and then 4 pi here somewhere. So this will just be the same thing repeated again. There we go. And similarly, if you go backwards, so if you start your angles going backwards that way instead, you'll just get the exact same form going here. So we'll go down first, then through the middle, then up, then back down. Oops, it's not perfect, but there we go. So this is our sine graph, and from before we saw our cosine graph, which is similar. So once again, it's got a maximum of 1, minimum of -1. So this is x, equals cosine of theta. This is theta along here, the angle. So this time we start at 1. So you see the cosine, the x-coordinate starts at 1. So let's put in our different points, pi on 2, pi, 3 pi on 2, 2 pi, and similar going backwards, negative pi on 2, negative pi, negative 3 pi on 2, negative 2 pi, and this will just, these points will keep going. So start here, then it will go down here, then this is the next point, back up like a wave. So if we join those up, there we go. And similar here. Okay, there we go. So there's a few different things we notice about these graphs. Firstly, they're exactly the same, except cosine starts at this second point here. So this second point is where the cosine graph starts, but apart from that, they're exactly the same. And I can keep adding more points on here if I want to. Depending on how big my domain is, of course. These will just keep on going like waves forever. Okay, so they're the same. You also notice that we have a maximum value of 1. So let's write the maximum value is 1. The minimum value down here is -1. And you can also see the average value, or the point that it sort of oscillates around, is 0. So let's call the average the mean. The mean value is 0. Now a couple more words. Because the maximum is 1 and the minimum is -1 and the mean is 0, we define the distance between the mean and the maximum, which is also the same as between the mean and the minimum. We call that the amplitude. Amplitude. It's a useful thing to remember. So in this case, the amplitude is 1 because it goes from 0 to 1, which is the same as the distance between 0 and -1. So that distance is the amplitude. There's also another word. So you see that this thing repeats. Okay, so here's one lot of it, and then it's repeated here. It's repeated, and it's repeated over here, and it will keep being repeated. Each one of these repeats is called a period. A way that you can find the period is going from peak to peak. So that's the period. It's just however long it takes to repeat. Or the period goes from this point. So the reason we go from peak to peak, because if you think about going along this axis, you'll hit this middle point. So the period is this distance. So, because that's the whole thing, with the maximum and the minimum included. So that's the period. And in our case, we have a period of 2 pi, because it gets repeated every 2 pi. So there we go, there's a bunch of different quantities we need to be able to remember. Okay, so there's our basic forms of a sine and a cosine graph. Next, what we're going to be thinking about is, just like with all other graphs, we're going to be thinking about dilations and reflections and transformations. Okay, so first we will do dilations. Now let's consider y equals 2 sine x. You can use x or you can use theta at this point. Okay, it doesn't really matter. Okay, so y equals 2 sine x. Let's just plot that and have a look. So get out our cas. Here's y equals sine of x. Now I'm going to plot, so tab for a second plot, y equals 2 times sine of x. Let's have a look. There we go. So it's the thing that's changed is the amplitude, and the amplitude has increased to 2. Okay, so this number out the front here is a dilation from the x-axis of 2. So it's increasing the amplitude. So let's do a quick sketch of this. So that is now at 2 and minus 2, and it will look something like this. Sorry, they're all supposed to be at the same points. Okay, so if we have, let's do a general case, if we have y equals a sine x, or y equals a cos x, the amplitude equals a, whatever this number is out the front. So let's do one extra example. Let's suppose, let's plot another one. So let's say we have cosine of, let's say, half, oops. So I mean, let's do the half first. Half cos x. Cosine x. Give it a test. Yep, so there we go. So the amplitude is now a half. It's half as big as our original blue one, and it's a cosine graph, so it starts at a maximum. So there we go. Our amplitude is a, this number out the front here. Okay, so they're the basic type of the amplitude changing dilation is quite easy. Now there's a second type of dilation which will change the period. Whoops. Okay, so let's do another example. Let's suppose we have y equals sine of 2x. Okay, so y equals sine of 2x. Now let me get some more space so we can think about this a bit more sort of cleverly. Alright, so we've got y equals sine 2 of x. Let's suppose, let's let a, or alpha equals 2x. Now if we do a graph of y equals sine of alpha, it will look like a normal sine graph. Okay, so here's alpha, and it cuts through at pi on 2, and pi, 3 pi on 2, and 2 pi goes up to 1. Oops, positive 1 and negative 1. There you go, so these are our important points. Alright, so there's a sine of alpha. Now, but we've said that alpha is 2 times x. So how do we get 2x to be pi on 2? Well, so we're saying that 2x has to equal pi on 2. So what that means is that x equals pi on 4, just rearranging it a bit. So if now we wanted to plot our graph but with x, so we've got now y equals sine of 2x. What's happened is pi on 2 has become pi on 4. Pi, so we're now saying 2x equals pi, therefore x equals pi on 2. So instead of being pi, that point is pi on 2. So let's draw this out. We've got pi on 2 instead of pi. We've got pi on 4 instead of pi on 2. We're going to have 3 pi on 4 instead of 3 pi on 2. And instead of 2 pi, we're going to have 1 pi. In other words, all of these are being halved. And then we're going to have the same shape. Like this. So what's happened is it's been squashed. This one's been squashed. So let me show you this using our CAS calculators. So So first let me just draw just a graph of y equals sine of x. Now our next graph will be y of sine of 2 times x. And you'll be able to see the squashing effect. So the pink one's our original, and this green one, it's been squashed. In other words, the period is half as big. Okay, the period is half as big. Now imagine if we instead had, because that's sine of 2x, imagine if we had sine of half x. So let's try sine of, let's just make it 0.5 for half x. There we go. So now the period is twice as long in yellow. So what we're doing here is we're either squashing or stretching our graph. So we can say if we have y equals sine of a times x, or if we had y equals cos, let's make this a b actually, we've used a already, let's make it b of x, then our period, instead of just being our original period, if we had just y of sine of x, for instance, our period was, period is 2 pi, but now with this factor of a b, our period is 2 pi divided by that b. In other words, it's being squashed. So it's if b is like a large number, like 2 or 3 or 4, it's being squashed. If b is a fraction, like a half or a third or something, then it's being stretched. Okay, so let's write that back where we were, so we can. Okay, so back in our dilations, our new piece of knowledge is that if we have y equals sine of bx, or y equals cos of bx, the period is 2 pi on b. So there we go. So those are our dilations done. So this one is making the amplitude go up or down. So making it get larger or smaller in that way. And this one is the dilation in the other direction, making it either squashed or stretched. So here if a is a large number, it gets pushed up, but if b is a large number, it gets actually squashed in. So there you go, a few things to remember. Now, second thing, reflections. Now reflections are fairly easy. Basically, if there's a negative sign, it will just be reflected across the x-axis. So let's just do an example. For y equals negative sine of x, instead of the graph, let's plot it. In fact, let's just plot this one. So here's our original graph, sine of x, and I might even zoom in for this. Okay, so there's sine of x, and now let's do another one, which will be negative sine of x. Sine of x, and there you can see what's happened. Instead of this graph starting at 0 and then going up, it's now starting at 0 and going down first. So it's been reflected across the x-axis. So let's just draw a little picture. If there's a negative there, then sine x actually goes underneath first, and so on and so forth. Or if we have y of negative cos x, instead of starting at positive 1, everything's reflected and now starts at negative 1. Okay, so there we go. That's been a reflection in that direction. Now, very last thing is a transformation. And these work pretty much exactly the same as every other transformation you've seen. So if we had y of, say, sine of x plus a number, so let's say 3, what's happened now is our mean value, our mean is equal to 3. So the graph now looks like, well, it will now look like this. Let me just undo that. Okay, so it used to be that our graph would oscillate between start at 0 and go up to 1 and then back down to 0, then down to -1. But now everything's been shifted up 3. So instead of the mean value being 0 along here, the mean value is now at 3. It's been shifted up 3. So I'll just put a dotted line to show my mean value. So then, sine of 0 is now 3 instead of 0. Then at pi on 2, instead of going up to 1, it now adds 1 to 4. So it goes up there, and then at pi it's back to 0. 3 pi on 2 is now down to 2, because it's 3 minus 1, and back to 1 here. There we go. So it's exactly the same shape, but everything has been shifted up 3 units for that one. Now if it was a minus, everything would just be shifted down, of course. So for transformations, suppose we had y equals sine of x plus c. That is, we now know that the average, the mean value is at c. So it's been shifted up c units. Up c units. There we go. Okay, so we've done dilations, reflections, and transformations. Let me just summarize those 3 things for us so that we've got them all on the one page ready to go. Okay, so for our, so let's suppose we have y equals a sine b times x plus c, or y equals a cosine b times x plus c. What that basically means is we now have an amplitude of a, period of 2 pi on b, and a mean value has been shifted up c units. So that's the a, the b, and the c. So there we go, that's all the new content. Let me just do one quick example for us. So let's suppose we have example 1, plot y equals, let's say, 3 cosine half x plus 1. There you go. Y equals 3 cosine half x plus 1. Okay, well what I've got here is I've got the 3 means amplitude is 3. So let me just write this out. Amplitude is 3. Well, maybe I could write amp. Amp is 3. The period is going to be 2 pi divided by a half. So the period is going to be 4 pi. 4 pi. Because that's 2 pi divided by a half is 4 pi. And the average, the mean, I should say mean, is 1. Okay, so let's do all of those things. Here we go. Set of axes. Okay, now I'll do my dilations first. So first I'll show my period of 4 pi. So it's going to have a period of 4 pi, and then it's going to repeat after that. So I'll put my 4 pi here. Now there's going to be a halfway point. It's sort of split into 4 quarters. So the halfway point is going to be 2 pi, and then we're going to have pi and 3 pi, split into quarters. Now, and then it will go up more as well, and also down. So this down value, that'll be negative pi, that'll be negative 2 pi, negative 3 pi, and so on. Now I'm also going to show my So my amplitude of 3, that will sort of come in a moment, and my mean is 1, so it's actually going to be 1. It's going to be up 1, 1, and with an amplitude of 3. So from 1, it's going to go to 4, and if you take off 3 from 1, it's going to go down to -2. -2. Okay, so now we're ready to show the graph. Now we remember that a cosine graph starts here at the top and then goes down like that, so keep that sort of in mind. So we're starting here at the top, there's no negative sign, so it's not reflected, and then the next one will be here down, and then it'll keep going down, then we'll be back to here, and then back to the top. So that's what the period is. You see that we've done one full thing, it's reached the crest again, so that's 1 period's worth. So let me fill that in. And then it will repeat. So this one will be here. We have the next one down here. Next one will be here, and so on. You know, and that will repeat that way, and this one will repeat in the other direction. So here, 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 and so on. So there we go, and we've finished. We could continue this indefinitely in both directions. There's no point at which this will stop, unless someone has put a domain restriction on your question. So there we go, sine and cosine graphs. See you later.